This is the review session for the December round silver contest. Many of you have done it. Hopefully you have learned how this feels. For silver level contests, the passing threshold actually is in 9, whereas the average 750. The gold actually was a little bit harder, 700 rather than the 750. I know many of you were saying, it is actually harder than I thought. The passing threshold should be less than 750. Well, since many students did do well enough, so the threshold is not lowered. Hopefully you can learn from the examples, because USACO past contests, especially in the most recent seasons and most recent rounds, should provide the best approximation for what will come. So if you think you did not do well enough in the December round, then study the problems and hopefully learn what you can do better, and then prepare so that you can do better in Jan round. To many of you, I have been saying Jan round probably would be the best chance, because December round you were just off the final exams. You did not have much time to prepare. After the winter break, you have done intensive training, hopefully for some of you, right? And keep the momentum. So if you can, make it an average hour and a half on every day, or if you can afford, right? Maybe in the first 3 weeks from now till Jan 27th through 30th. 2 hours a day would make you better prepared, so that when the contest comes, you would be in the best status to take the challenge. Again, we're going to try to go through maybe 2 questions if we can. And then the third one, we try to make videos available again for all the okay, so let's get started. The 3 questions, I think, right, the first one would be easy, and that is also true to many students. So barn tree, okay, refresh your memory. We have n barns, n can go up to 200,000. So you're going to read up to 200,000 integers, and then each edge here, right, you're going to read the 2 numbers. So here actually you're going to read up to 400,000 integers. So here clearly, for those of you, right, still writing in scanner, then it's probably going to run out of time if you do the scanner. So here, that's another case. Please switch to buffered reader if you're writing in Java. C++ actually does not matter. C is efficient enough. But for this question, the time limit has been doubled. So 4 seconds for C++, 8 seconds for Java and Python. Memory also, the limit has been doubled from the typical 256 megabytes to 512 megabytes. All right, so you're given a tree. So there are n nodes and n-1 edges, so that every 2 nodes are connected by a sequence of the edges. And at each node, we have the HI hay bales. HI can be a number between 1 and a billion. And it's guaranteed the total number of the hay bales is a multiple of n. So we want to make sure all the nodes have an equal amount of hay bales. So how can you make all the nodes have the average number of hay bales and try to achieve this status using the minimum number of the moves? So every move you can, in every move you can transport X hay bales from, say, node A to node B. But of course, you have to make sure X is no more than the number of hay bales at node A. So that's the question. We're going to answer what is the minimum number of the, you can say, orders each order you can move X hay bales from node A to node B. So that at the end, finishing all the orders you specified, then every node has the average number of hay bales. So you can think about it, this one, if a node has more than enough hay bales than the average, then you have to move it. But where do you move the hay bales to? And you have to make sure that your scheme, your idea should result in the minimum number of the orders. So suppose I do have here, so 3 here, 4 here, and a 2 here. I need to move one hay bale right from this node to this one, but I cannot move directly. I have to use this first move to say this is node. We're going to give the name right. So this is node A here, node B here, node C here. So I need to use A as the bridge, right? I'm going to move one hay bale from node B to node A. So this becomes 3 and this becomes 4. Now I'm going to move one hay bale from node A to node C. So this becomes 3 and this becomes 3. So now they would all be the same. So that is obvious, right? When you try to make it say, what about this one is say, start not from 4, 3, 2, rather say 30, 40, and then 20. So the same configuration. So do I move one by one? You don't, right? You're going to say, find out the average. If this one is bigger than the average 30, I'm going to say move 10. So this will become 30. This becomes 40. And then move the 40 to, move 10, right? From here to here. So that still would be 2 orders rather than say 10 here and 10 here. That's 20, right? Of course, sometimes maybe the order would be restricted. Every time you can only move 1, then of course will be, will take more orders. Here, you can do any number of hay bales as long as X is bigger than or equal to 0 and less than HA. Of course, you will never try to do an order where X is 0 because that means you do nothing. You can always remove or eliminate that order. Okay, so roughly you got the idea, right? I need to go from, move the hay bales from a node that has a number that is above average. So how to get the average? That's it, right? I'm going to go through all the nodes and add the number of hay bales together. So I get a total divided by n. So this will be the average. Now I'm going to go through, right? If a node has more than average, then I'm going to move it away. Well, this one is easy, I know. But sometimes I may have the scenario like this one here. So this one does have 40. Do I go this up and go down here? Or do I go down here? So you have a, let me use different color. So this is node A, node B, node C, D, and E. I may have to move some hay bales up. I may have to move some of the hay bales down. How do you split? Right, I did not even use the number of hay bales at below. If this one is 30, then make sure it's not. For example, I would go 40, 30, 20. If I go, that's 5, 35, and 30 here. If I move this one 30, then you don't have to go down. 42 here, and this one say 28. So I need to, right, you see here, I need to move 10 up from B to A, right? Then this 10 will be passed to C, so we'll make this one 30. And then I need to move 2 down here to make this one 30. But then how do you know, right? When I process this one here, this one has 42. How do you know this one you have to move 10 up and move 2 down? that would be hard, right? Of course, this one is easy to see. But if you work with the tree at each node, right? If this one is above the average, how many you're going to move up, how many you're going to move down, and actually move up, that's fine because every node has only one parent, that's easy. And move down, okay, maybe this one is 29, this one also 29, you're going to move one down here, move one down here. And could it be more complicated, right? You may have to go down further. So that could be a dilemma. At each node, when we visit the tree, the nodes in the tree, how many should we move? Actually, you can think about another way. Suppose if the move does not have to be always move the cows, hay bales, right, in positive quantity, I can move negative quantity of hay bales. Okay, probably you have worked on a question that I talked about maybe a year ago in the open session, maybe in the silver or gold. That is very similar question, but rather than working a tree, you're going to work with an array. So suppose A here, and you have the numbers A1 through AN. Again, want to make sure all the numbers will be equal. Each time you can move any number of the, say, hay bales, right, from one position to another location. Of course, at 1, you can only move to the right. At location N, you can only move to the left. Otherwise, in the middle, you can move to the left. You can also move to the right. And also, right, you can say this position I, you can move to I minus 1, move to I plus 1. Also, position I can accept hay bales from position I plus 1, accept hay bales from I minus 1 anyway. So you can do either way. Again, find out the minimum number of the moves so that all the numbers will be equal. Of course, right, make sure if you say initially, you add all the numbers I from 1 through n here, right? This number is a multiple of n so that you can do it, get the average. So provided this is the case, report the number of the minimum number of the moves so that all the numbers will be level equal. So for such a question, normally we're going to say sweeping. So start from A1 here. If A1 is above average, you're going to move hay bales from the left to the right. What if AI is less than the average? We still do this, but rather than moving positive number of hay bales to the right, you're going to move negative number of hay bales to the right. Okay, that is fine. That will give us the minimum number of the moves. But here you have to make sure, right, when you move the hay bales, you have to move positive number of hay bales. And you have to provide such a sequence. The sequence of the orders, right? Clearly, it's not unique, but you do have to provide a valid sequence of the moves. So maybe a little bit different than this one here. This one is a simplified version, right? Rather than say moving the number of the positive hay bales, you can say spread out. You can say move a number can be positive or negative, eventually make all the numbers equal. So that is fine to find out the minimum number of the moves. So here, a little bit harder or complicated, not harder. So the idea for this one is at each node, suppose the node is X here, we're going to find out the total number of the hay bales in the subtree where X is the root. You say, how do you know X is the root of the subtree? Well, you always pick one node as root. In general, you can pick node 0 as the root of the tree. Root is this one here, not this root. Okay, want to make sure. Normally we say in CS, right? We say this is spelled as pronounced route, and this is root. So root of the tree. Once the root has been decided, then for each node X, right, you can, there is a unique way to interpret the subtree where X is the root. Okay, so now for each node X here, we're going to find out the total number of hay bales in the subtree. if the total number of hay bales in the subtree is bigger than the expected share, that means, right, the total here, if it is bigger than the number of the nodes in the subtree times the average, then you know, right, eventually I have to move the hay bales from this node X to its parent. If you have more hay bales than the expected share, then you have to move the hay bales up. What about if the total number of the hay bales is equal, then you don't. You don't have to move the hay bales from X to the parent because, right, that's just exactly perfect. Also, another case would be if the total number is less than the number of nodes times average, then you need to get help from the parent. You need to move hay bales from the parent to node X. But then it will make a difference, right? You cannot say, okay, if it's negative, you cannot process this one first. Why? You cannot move negative hay bales to the parent. As we did here, right? Here you just sweep from the left to the right, just one round of traversal. That's enough. Here you have to wait until the parent node P gives enough hay bales to the subtree so that it can distribute the hay bales down, so that make sure the subtree would be balanced. Here, when I say balanced, right, eventually every node should have the number of hay bales would be just average. So here we're going to process in this way. For each node X here, first we're going to do the counting, the total number of hay bales in the subtree. If this one is bigger than the expected share, so we have the child C1, C2, C3, and so on. So for each one, find out, right, hey, for this child subtree, do you have more than the average hay bales? If you do, move it back to X here, because X may have children that has less than the average number of hay bales. So for all those that have plus hay bales, move up to the parent X. For those child nodes, if they have less than average nodes, right, they would get help from the X here. They would get help from parent X. You say, well, what if the subtree at X, right, has less than enough, as we saw here, right? X has to get help from the parent. Well, we start from the root of the tree. So suppose X is the root, it does not have the parent. Then we know, right, this tree must be balanced, because here, the whole tree must have the total should be average times n number of nodes, right? So when X is root, the tree must be even. That is, the total is equal to number of nodes times average. So it does not need to get help from the parent, does not to contribute to the parent, because for root, it does not have a parent. But after that one, then you know, right, for the root, if some children have plus more hay bales than average, then you must have a child, right, that has less than average, must be balanced. So we're going to do this one here. For all those children, when they have extra, they're going to move back to the parent, and then they will be used to help the children that has less than average. So that's the idea. So this will make sure we don't have the awkward situation. You can move negative number of hay bales from one node to another node. So move these plus first, and then move down the negatives. Okay, one trick here is you don't have to actually work with the average. So for each hay bale, the number of the hay bales at each node, right, we're going to say minus average. once we have obtained the average, we're going to say update HJ is assigned to HJ minus average. Then if a tree is balanced, then the total number must be 0. So some of them would be positive, some of them would be negative. If you add them together, it will be 0. So that is a typical way to make life a little bit easier, so easier to state. Okay, so let me go through one implementation. The traversal. Okay, so here, bond tree. Again, we're going to declare the hay bales, make it long, because I may, if I add enough, I could make the number bigger than the integer maximum. So make this one long. And then the total, again, the number of the hay bales in each subtree, where X is the root of the subtree. That's the adjacency list, average here, and then also the orders. Orders, we're going to keep this one as source to destination, and then the number of hay bales. And we're going to keep this one as an array list of integer, non-array. So this will contain 3 elements. N is number of the nodes. H would be the number of hay bales at each node, and the subtree total. And for each one, right? For each X here, we're going to say how many hay bales in total in the subtree where X is the root. And if we do this one, this is 0 indexed for each node. So for each one, we're going to read the number of hay bales, HJ, and then this average is actually now acting as the total divided by N. So this will become the actual average. And then I don't worry about, say, what if this total is not a multiple of N? That's not the case. It's guaranteed. Total is always a multiple of N. So we have the actual average. That is an integer. And we're going to subtract the average from each HJ. Now, if you do the sum, the total number of hay bales in the whole tree would be 0. Okay, that is clear. And we're going to read the adjacency list, the N minus 1 edges. Again, this will make it 0 indexed here. Add U and V to be the neighbor list of each other. Now we're going to do the 2 graph traversal, DFS1, DFS2. Okay, DFS1 is we're going to find out the total number of hay bales in the subtree where X is the root. Okay, so X is current node and then parent is the PAR. First, the number of the hay bales in the subtree, you have to add HX, right? So the subtree started from X, so add it here. Now we're going to do this one recursively. For each child or for each neighbor of X here, if the neighbor is not parent, then we're going to call DFS1 for child and X is the parent. After we have done the parent, the child node here, now the subtree total of X, right, should be increased by the subtree total from the child. Okay, make sure this one is in right order. You have to do this one recursively first. And then once you have the total count for child, you're going to add it to the total at X. Okay, so this one is kind of straightforward. Many of you have done this DFS. And don't think this one is straightforward, but will be used a lot for graph traversal, not only at silver level, but also at gold and plat. Okay, make sure those recursive routines or functions, right, you can easily implement without bugs. DFS2, now this time we're going to run another traversal so that we're going to distribute the hay bales so that the subtree where X is the root, right, has 0 hay bales at all nodes except possibly at X. Okay, every other node should have 0 hay bales except maybe at the root. You might have more positive. Okay, now for each child of node X here, of course, right, child cannot be parent. So if this child subtree has positive or 0, we're going to visit it, we're going to distribute. If it has 0, that's fine, nothing important. But if this subtree has more positive total number of haybells, that means right, it has extra. Those haybells should be moved from child to X here. So these are the ones we just mentioned, right? So this child subtree has more haybells, so they should be moved from child to X. So this will be one order. So we're going to add one entry here, move from child to X. How many haybells? That's what we have left here in the child subtree. If this one has 0, right, you don't add an order. Only when this child subtree has more haybells, then we're going to add an order. Okay, so these are for the children subtrees, the child subtrees, right, with positive haybells. Okay, now we have to use the extra, the plus haybells, right, now have been stored at node X. Now we're going to distribute those down to the children where the haybells would count as negative. So now if child is not a parent, always, right, avoid the parent because parent should be processed earlier. And then the subtree where child is root, right, has negative number of haybells, then we're going to add a node going from X to child. And then the number of haybells we need to show, this one is in need of so many haybells, right? That is a negative number. So we're going to say move so many haybells from X to child. So now this child subtree should have just enough to fill the holes so that the negative numbers, right, will be 0. Once the child subtree, right, the child node has these haybells, then we're going to do the DFS. So here the order, this one we're going to do the DFS first and then move. The order, I mean the order would be reversed. You have to give the enough haybells to the child so that we can distribute. This one you're going to distribute first and then move the extra haybells from child to X. Here, just because we cannot move negative number of haybells from one node to another one. Oh, why? How many extra, right? So here, if this child subtree, right, has been processed, so child may have extra haybells, or the others, right, should have 0. So here, X is here. This is child C1. The subtree here has been processed, DFS2 here. So all these guys and going down, right, they have just 0 haybells. But this one may have positive. So if this one still has positive haybells, these positive haybells, right, should be moved to X. That's why we're going to say send these many haybells from child to X. Not more, not less, right? So all these have been set to 0. And if you move the extra haybells right now, C1 also should have 0 haybells. The extras will be stored at node X. Node X, again, these haybells, right, should be distributed to the other the child subtrees where the number of haybells should be negative. Because if you have positive, then must have negatives to cancel each other. Okay, the same thing here. How do you know exactly how many haybells, right, to move? So here, this subtree is in need of so many haybells, then we're going to move from X to child exactly these many haybells. So not more, not less. Make sense? Good. Okay. All right. Let me also briefly go through the barn tree, the C++ version. So here, DFS1, the same. Yeah, this piece of, this part, right? The body of the DFS1 is exactly the same as the Java code. DFS2, also pretty much the same. Yeah, the same thing. Here, you can use pushback, you can use in place back. In place, you can just provide the input. If you do pushback, then you have to create an entry, an object. In general, if you work with the multiple input, then it's better to use in place. Actually, it will be more efficient than pushback. But if you say add just one number integer, right, then that's not making any difference. Okay, so that's for DFS2. And oh, there's one thing here. Notice right here, I'm using a tuple. In a tuple, you can have different types. That's regular integer, that's long integer. So you can have multiple types. So that is actually convenient. Notice what I did in Java, right? I have to make all of them the same type, so make them long integers. If you have just two, right, you can use a pair. Pair is convenient. The others would be roughly the same. Yeah, DFS1, DFS2, and then now the orders size, right, would be the minimum number of the moves necessary. And then for each move, you're going to go from node A to node B. Here we have made them to be zero indexed. Start from 0, that's 0 indexed. So you have to make, when you print out, right, you have to make it 1 indexed. So that's why you have to do +1 here. Q is number of the hay bales. So just want to mention here, at gold level, we do have another way to make it maybe more straightforward, and that's called a topological sort. Topological sort to avoid the dilemma. So move a negative number of hay bales from one node to another node. Or which one should be processed first? So the two issues can be resolved using a topological sort of the graph. Here, of course, the graph is a tree. Okay, keep in mind, you're going to, you can revisit this question after you have learned how to do a topological sort. Okay, so that is for the first problem. Again, depending on the pace, right? We may be able to finish 2, and if we cannot, that's fine. Okay, second question, circular barn. Okay, when I saw the question, I thought they should make it a little bit easy because we did have circular barn question, I think in season 2016. Now, I thought they would use circular barn 2, circular barn 3, and so on. That's actually the tradition. Now, if I say, okay, did you work on the question circular barn? And you might ask, right, which season? Okay, so now I have to say circular barn season 2023. It will refer to this one. Circular barn season 2016, right, will be another one. Okay, so here we have n barns, n rooms. N can go to 10.5. Each room has AI cows. Every time Fj or Fn, farmer Node or farmer John, each can remove P cows from the room. P can be either 1 or a prime number. And the farmer, the person, the player, right, would lose if it's this player's turn, but there's no cow to remove in the room, then the game ends. So here, kind of surprising, why this number P must be the 1 or prime number. This got many students confused. What does it mean? Actually, this is a place you're going to notice when you have the 1 and the prime number, then you're going to study the number, the integer 4. Okay, you say why 4 is critical here. So for all the primes except 2, divided by 4, the remainder is either 1 or 3. Suppose AI is a multiple of 4. The second player always would win. All right, so suppose the first player take 2 out. The second player also can take 2 out. 2 is a prime, right? If the first one takes a number that is, say, p congruent to 1 mod 4 here, then player 2 can always take and say 3, right? If AI is multiple 4, after you take p Hebels out, right, then the remainder must be 3 here. So player 2 can always take either 3 or take a p that is congruent to 3 mod 4. So every time p2 will still guarantee 4 divides this update AI, right? AI would keep decreasing, but player 2 can always make sure this AI, the number of the cards running in the room always is a multiple of 4. So eventually AI would be 0. So P2 would be the last one to make AI 0. And the next time P1's turn is right, then P1 will lose. So here, whenever AI is a multiple of 4, then the first player, Farmer John, would lose. Now the same argument, right? So if 4 does not divide AI, then Farmer Node would lose, because the first one is always, Farmer John can always make, right? If AI has remained 1, then player 1 can just remove 1 or remove a number p that is congruent to 1 mod 4. Leaving the result, right? Now, after you've done this one, then AI is multiple 4, then Farmer N would be the first one to go, and Farmer John would be the second one to go, then Farmer John would win. So here, this is why the reason, right? We're going to talk about the divisibility of AI by 4. Okay, so this is actually, if you have been through the math training, then you're going to notice this pattern. Of course, if you have seen it before, then yeah, I would say that's not hard. But if you have not seen it before, then this could be a obstacle and could have you stuck or get you very upset. You're right. We're going to assume each player will do optimally, right? From this analysis, right? If AI is multiple 4, then the second player will win, right? I'll always keep it AI is multiple 4. Then the second player has the final say to make it 0. Now, if AI is not a multiple 4, then the first one can make the AI multiple 4 after his move. Now he becomes the second one, right? Because the opponent will be the first one to go, and then the he will have the final say to make it 0. Then he wins, right? So easy to see. Now we need to for the n numbers, we're going to count each AI, how many turns it will be 0. So for each AI, we're going to calculate the number of turns to make it 0. So for the winner, if AI is a multiple of 4, the winner will try to make it to 0 as fast as possible, because it's guaranteed, right? If AI is a multiple of 4, then the second one is the winner. So the second player will try to decrease this one as fast as possible. Then next time, they come to this room I, then the first player has nothing to do and then will lose, right? So the winner will try to decrease this to 0 as fast as possible. For the loser, then try to delay this as much as possible, because you have the chance, right? For the other rooms, the opponent may lose, right? You see the argument. So maybe this is a dangerous zone for player 1. But player 1 says, okay, maybe there is another one, right? And then player 2 would have the danger. If I can delay the process, maybe I can say this will take, say, 10 turns to reach 0, but this one will take just 9 turns to be 0. Then at 10th turn, player 1 will lose. But before reaching the 10th round, player 2 would lose at 9th inning, the 9th round, right? So for the loser, we'll try to delay this as much as possible. For the winner, try to decrease this one as fast as possible. Okay, we're going to always go this clockwise way, the circular one. Okay, so now for each one, we're going to count the number of turns to 0. And here the difference, right? For the winner, try to make it minimum number of turns. For the loser, try to make it max number of turns to 0. So here you can see, right? For the winner, if you want to make it decrease as fast as possible, you're going to get a prime P, right? So if AI has remained 1, so if AI is congruent to 1 mod 4, then the winner, right, will get a prime that is also congruent to 1 mod 4, so that AI would decrease by P, right? You're going to get the maximum P so that this will drop as fast as possible. When this one is 3, we'll try to get the prime so that this P is congruent to 3 mod 4 and then subtract. Of course, when this is, say, AI is an even number, to make this one the status, right, then P must be 2. All right, so now you can actually see, right, if AI is even, the number of turns to make it 0 is always AI over 2. Okay, just do this one a few rounds and you can see this one here. So if AI is indeed 2, right, then the winner is the first one. So P1 will just get 2 and then it's done, right? So A is done. So this would be PI will take 2, choose 2. And then the number of rounds, number of turns, right, would be just 1 here. If AI is 4, the same. P1 still would take 2. Oh, I'm sorry. This one would be P1 would lose. So no matter what player 1 does, if player 1 takes 1, player 2 will take 3. Player 1 takes 2, player P1 is 2, P2 also is 2. P1 is 3, P2 will be 1. You cannot take 0, right? P1 cannot take 0. So this one will lose. Anyway, this would again would be 2 rounds. Then we're done. 2 turns. And if AI is 6, so here P1 is going to win. So P1 will take 2. And then now left with 2, right? So this would be 3 here. Again, if it's 8, P1 would lose no matter what P1 does. Actually, P1 try to delay. So P1 will also take 2 to make it 6. 6 will take 3. So that's before here. So it's always the case. If AI is even, the number of turns to make it 0 would be just N over AI over 2, half of the number. Now, if AI is odd, then the first one always wins. So you're going to always, AI is odd. So you're going to first get the biggest P so that P congruent to AI mod 4. Now AI minus the P is even. So you're going to say the number of turns to make it 0 would be half plus the 1 you're going to choose P, right? So this would be the number of turns to make AI to be 0 when AI is odd. So now for each AI, we have the number of turns to make it 0. Now for all the AIs, you have this count, number of turns to make it 0. Now you can find out the first one, the minimum, the number of turns to make it 0. Right, so maybe this one, the 10th, this one, the 9th, maybe this one does not matter, right? Suppose this one takes 7 turns to make it 0, then they would be safe. Why? Because when before they reach the 9th turn, the 10th turn, right, this one will make one of the players lose. So now when the number, the minimum, right, if it is odd here, 7 turns, so the first player has the final say to make it 0, right? Because every time 2 players will take turns, right? So player 1, player 2, player 1, player 2, P1, P2, 6 rounds. The last time P1 has the final say, you're going to repeat 3 rounds, 6. The last time P1 has final say, so P1 will win. If this one is 6, then P2 will win. So P1, P2, P1, P2, and then next time P1 comes here, right, will be 0. So depending on the smallest number of turns, if this one is odd, player 1 wins, otherwise P2 wins. So we can find out the smallest one, okay? So let me go through the implementation. So here, okay, I'll go through this circular. This is the place you can find out the primes. So you're going to do the sieve method. So sieve method, many of us have done it, but we said, right, for silver before, we have never seen any question. You have to explicitly use this technique, but now you have such question. Number of turns to make it 0. So here, winner to minimize this number, loser try to maximize. So we can find out the number. And this is sieve method to try to find out each number x, right? Is it a prime? And maximum prime to make to be congruent to this number 1, 2, 3. 0 is actually just for convenience. It's actually not the maximum number to make it congruent to 0 here. So this one is extra, is just for convenience, hopefully to make this formula systematic. Okay, so here the sieve method here. From composite here, initially every number is false. Is it a prime? False. Now, start from 2 here. If it is a prime here, not a composite, then we're going to mark every multiple, every proper multiple of I to be composite or non-prime, right? Composite J would be true. Now, if this is case I is a prime, then we're going to say I mod 4, right? So I and I mod 4 should be congruent, mod 4. And this would be, so far we have seen the biggest prime to have this remainder, the maximum prime, so that the remainder is P mod 4, the same thing. Okay, and then the number of the turns to make this integer I to be 0 would be just exactly as explained. When I is even would be half of it. When I is odd, you're going to find out the biggest prime having the same remainder divided by 2 plus 1. Okay, so this part, right, that's the sieve method. And then we're going to process for the Q queries. So for each one here, answer is the minimum number of turns to 0 at the first occurrence. Now for each one, actually this one does not even save the array of AI, just read the AI. And for each AI, find out the minimum number of find out the number of turns to 0 and make sure this one is the smallest one. And if they have divided by 2, why? Because there are 2 players, right? Take turns. So divided by 2, if they have smaller one, then we're going to take that one. If they're equal, we don't. Divided by 2, the number of the rounds, the minimum number of rounds. If they have the same number of rounds, we don't mind. Okay, it will be the same. Whoever comes first would be the first one to go. Only when the number of rounds is smaller, we're going to update it. So at the end, if the number of the round turns, if it's odd, then FJ, the first player, has the final say. Otherwise, farmer node has the final say, and then node will win. So for each one, we're going to print the answer. Actually, for this one, probably the same for C++ does not matter, but for Java, probably it's better to have a string builder because n can go to 10.5. So the output may have 100,000 lines. So did I implement that one? So, circular barn. I did not. So probably this part will affect the performance. I think this one has, no, it did not have the double time. So if when you submit your answer and you run out of time for some cases, then try the string builder. String builder will concatenate the results to the string builder and then just print out once at the very end. Mod 4, because at the, okay, you're talking about this one, right? I need to find out the biggest prime. So if say AI is odd, remember, right, then player 1 would win. But the strategy is you're going to find out a prime P so that P and AI would be congruent mod 4. So that after taking this prime P, AI minus P, right, the remaining number of hables, now this is even. This one is actually not even, just even, right? This would be multiple 4. If AI and P are congruent mod 4, AI minus P now is multiple of 4. So player 2 will go first and player 2 will lose, right? So how many turns? You're going to do 2, half of this one plus the 1, 1. So this will be the number of the turns to make AI 0. So I need to get the maximum P, right? Since player 1 is the winner. So player 1 would try to shrink this one as fast as possible. So he wants to get the maximum prime to be removed from AI. The maximum P less than or equal to AI. So that this is true. So that's why I need to have this mod 4. All right. Okay. So the second question, again, as I mentioned, right, if you have seen this before, working with primes and 4, this is not too bad. You have seen them before. But for those who are not familiar with the property, then this is hard, I have to admit. And then for the third question, actually, third question, range reconstruction. You should be able to realize once you have, say, the 2 numbers AI plus 1, you should be able to determine AI plus 2 uniquely most of the time. Just play with the cases and then you can realize the pattern. But again, this may take a lot of courage because during the contest, you may be nervous, don't have time to say, okay, in the next 30 minutes, I'm going to just play with a few simple test cases or the input, right, and find out the pattern, what is going on there. If you can do so, then question 3 may not be that hard. But again, we cannot be so picky, demand so much during the contest. Everybody is nervous, so this one is considered to be a hard one. Okay, for this one, we would also record a video, and then you're going to get the link for this video, the Zoom cloud. Again, let me go through this the list here for the questions for the classes for silver. Again, we have put them into A, B, C 3 levels. Last semester, if you were in bronze C, now you should take silver A. I'm saying this one, whether you get the promotion in the December round or not, you should consider silver A, or you say, I want to redo bronze C, that's fine. Actually, the bronze C, silver C actually would be, will have different problems. All the questions would be different in the curriculum. But last semester, if you were silver A, you should take silver B. Last semester, if you were silver B, now you should take silver C here. So give yourself some challenge. But if you say, I really get stuck at bronze C or silver C, I want to repeat, that's fine. It's guaranteed all the problems in bronze C and silver C in the spring semester and also fall semester, they will be different. So you should have more practice, but still the spring semester would be more competitive because you have 3 more rounds to come. And we want you to get the idea, right? Every round, you should see your score going up, even though it's not a definite or absolute indicator. If you get higher, then you get better. Not the case, because the questions do vary. Sometimes you think this is easy, sometimes you think it is hard, but for others, maybe the feeling is opposite. So still, on average, you should see the score increase every time you take the contest. And we have tried to make the classes to be reflective. So when we see the trend in the contest, we're also going to adjust, like I just mentioned, right, for the circular bond, the prime numbers, even though we did mention before, now we see the question does appear in the silver level for the first time. So we're going to maybe also talk about more in the upcoming silver classes. So even though the main theme would remain the same, but the questions, the practice, we're going to adapt. Hopefully we can help you to prepare for the upcoming rounds and get the promotion you were expecting. All right, that's all for today, and we're going to see you in the future.